The center of the Earth is a sphere of solid metal surrounded by liquid metal, spinning for 4.5 billion years without stopping for even a second. This iron ball is the size of the moon and sits 5,000 kilometers beneath your feet right now, with a temperature of 6,000 degrees, as hot as the sun. But here's what will blow your mind. If this core stopped spinning today, it wouldn't just be a problem for the center of the Earth, it would be the beginning of the end for everything on the surface. Birds would lose their way, technology would collapse, and solar storms would burn our atmosphere. How can something so far away and so deep completely control our destiny on the surface? Subscribe to the channel, leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. What sits at the very center of our planet, and what is it made of? Deep inside Earth, there is a solid inner core wrapped by a liquid outer core. The inner core has a radius of about 1,220 kilometers. The outer core forms a shell around it that is about 2,260 kilometers thick. Both parts are made mostly of iron. There is also some nickel and a smaller share of lighter elements such as sulfur, carbon, and silicon. These facts may sound simple, but they describe a place where matter is under conditions very far from our everyday experience. Pressure in the core is above 330 gigapascals. Temperature is roughly between 5,000 and 6,000 Kelvin. At those levels, even strong materials behave in ways that are only seen in experiments and models built for such extremes. The inner core is solid because pressure is so high that iron's melting point is raised above the actual temperature there. Under growing pressure, the atoms of iron need more heat to move freely. In the inner core, there is not enough heat to overcome that effect, so the iron stays locked in place as a solid even though the temperature is very high. The outer core is liquid because the balance is different. The pressure is a little lower farther out from the center, and the mix of elements there lowers the melting point. In that shell, the actual temperature is above the melting point for the mixture of iron, nickel, and lighter elements. The result is a liquid layer that can flow. Two boundaries define this system. The first boundary sits between the solid inner core and the liquid outer core. At that inner boundary, iron crystallizes. When liquid iron turns into solid iron, it releases heat. The process also pushes out some lighter elements from the solid as it forms, leaving them in the surrounding liquid. The second boundary lies at the top of the outer core. There, liquid metal meets hot rock. That contact is the base of the rocky mantle. Heat moves across this interface from metal into rock. The details of both boundaries matter because they set how heat leaves the deep interior and where changes in composition begin. They also set the space where the liquid can move. The sizes of the inner and outer core set the scale of any patterns that can form inside them. A layer that is thousands of kilometers across allows long paths for motion and for heat to spread. The total heat stored in the core is very large because the mass of metal is large. Heat does not move quickly through these depths by simple conduction. Rock and metal do conduct heat, but not at a rate that can erase temperature differences quickly across such thick layers. Because conduction is slow, even small differences in temperature and composition can persist and shape how the system evolves. Composition is more than a list of elements. It controls density, melting behavior, and how the liquid separates into lighter and heavier parts. Iron and nickel are heavy. Sulfur, carbon, and silicon are lighter. In the outer core, these elements are mixed with the metal. When iron freezes at the inner boundary, the light elements do not fit easily into the solid. They stay in the liquid and make it slightly less dense. At the pressures and temperatures present, even a small change in composition has a clear effect on density. Density contrasts are what let lighter material rise and heavier materials sink. This is a basic rule of fluids. In the core, such contrasts help set the large-scale structure of the liquid over time. The inner core, although solid, is not frozen in a single instant. It is still growing today. Growth is slow because heat leaks outward at a slow rate. As new solid forms at the inner boundary, crystals lock into place. The shape and alignment of these crystals can carry a record of how growth happened. Some studies suggest that iron crystals in the inner core may tend to align in certain directions, which could reflect how they formed under stress and temperature gradients over long periods. If such alignment exists, it is a clue to the history of the core because it hints at patterns of growth and stress that lasted long enough to leave a texture in the solid metal. The outer core is a region that can move because it is liquid. Motion needs room, and this layer provides it. The liquid can change its path as heat leaves the interior and as composition changes near the inner boundary. Where the liquid meets the mantle, the rock above is not liquid. The mantle is solid on short timescales, though it can creep very slowly on long timescales. That means the outer core sits below a boundary that removes heat but does not let the metal pass through. The rate at which heat can cross this boundary helps set how strongly the liquid is driven. If heat leaves faster in some regions and slower in others, the liquid below will adjust. The patterns that follow are not random. They are shaped by gravity, by rotation, and by differences in temperature and composition. They also respect the sizes of the inner and outer core. Pressure increases with depth. In the inner core, pressure is highest. This presses atoms together so strongly that only the hottest and most energetic conditions could let them move freely as a liquid. The fact that the inner core is solid tells us that the real temperature there is less than the melting point for iron under that pressure. In the outer core, pressure is lower, and the presence of light elements reduces the melting point further. The real temperature there is above this lower melting point, so the metal remains liquid. This explanation may sound short, but it reflects careful work. Scientists must balance temperature estimates, pressure profiles, and the effect of each lighter element on the melting behavior of iron and nickel. Each piece has uncertainty, but taken together, they form a consistent picture that matches many different observations. The path to that picture began with a simple idea. Materials under pressure and heat do not behave the same way they do at the surface. In laboratories, researchers press small samples of iron and iron alloys between hard crystals and heat them with lasers or electrical currents. They watch for signs of melting and measure how the sample changes. These tests cannot reach the exact pressures and temperatures of the very center of Earth for large samples, but they can reach similar ranges for very small samples and for very short times. Combined with models of how pressure grows with depth inside Earth, these data help set the limits. From those limits, the solid inner core and liquid outer core follow as the most consistent option. The presence of light elements in the core is also supported by mass and density constraints. If the core were pure iron and nickel, it would be denser than it is. Earth's mass and size are known, so is the mass and volume of the mantle and crust from seismic models. Those values tell us the average density needed for the core to fill the remaining volume. The measured value is lower than pure iron would allow. That gap is explained by the addition of lighter elements mixed into the metal. The exact mix is still an active question. Sulfur, carbon, and silicon are all candidates. Their shares may vary with depth. Each candidate affects melting, density, and sound speed in slightly different ways. Matching these subtle effects to seismic and laboratory data is how researchers narrow down the options. The two core boundaries are chemical and physical transitions. At the inner boundary, liquid turns into solid metal. At the outer boundary, liquid metal meets solid rock. The first transition releases heat and changes composition. The second sets how heat and any small-scale chemical exchanges reach the mantle. The shape of these boundaries matters too. They may not be perfectly smooth at small scales. Some regions could be slightly hotter or cooler, or slightly richer in light elements. Such differences would be small in absolute terms, but over long times they can guide where the liquid prefers to move and where the inner core grows a little faster or a little slower. Understanding these layers is not only about naming what is where, it is about seeing that structure controls behavior. The outer core can flow because it is liquid. The inner core can record growth because it is solid. The two boundaries set where energy and material are added to or removed from the system. The whole arrangement is large. That size means changes unfold slowly. Heat stored deep inside takes a long time to reach the surface. Changes in composition build up over very long spans. In this sense, the core is both active and restrained. It is active because metal and heat move. It is restrained because the scale of the system and the properties of the materials slow everything down. The numbers that describe the core may sound abstract, but they have clear meaning. A pressure of more than 330 gigapascals is a measure of how hard the weight of overlying layers presses down. A temperature of around 5,000 to 6,000 Kelvin is a measure of how much thermal energy the atoms carry. Together, they decide whether iron's atoms can move past each other or must vibrate in place. The radius of the inner core and the thickness of the outer core tell us how much space there is for solid and liquid, and how long a path heat or a parcel of liquid must cross to get from one boundary to the other. Each value sets a piece of the stage. The origin of this iron core lies in Earth's early history, when the planet was much hotter and materials could separate by density. Molten metal sank toward the center, while molten rock rose above it. As Earth cooled, the outer part of the metal core remained liquid, and the very center crossed the melting point and became solid. That is how a solid inner core can live inside a liquid core. The inner core's growth is ongoing because cooling has not stopped. Each bit of new solid at the inner boundary marks the fact that heat continues to leave the deep interior. This slow growth changes the composition of the outer core over time, because each new solid part leaves some light elements behind in the liquid. Because we cannot visit these depths, our understanding depends on how waves move through Earth and how tiny changes in rotation reveal motion below. Earthquakes launch waves that cross the interior. Some types of waves do not travel through liquids. Others do, but change their speed. Records from many earthquakes and many stations allow the outline of the inner and outer core to be mapped. These wave paths give sizes, shapes, and hints of texture. The length of a day also changes by a very small amount. Those shifts reflect energy and momentum exchange between the fluid core and the solid mantle. They show that the core is not locked to the rest of the planet. These clues are independent of drilling or direct sampling. They come from timing and from careful analysis of how signals change as they pass through different layers. Looking at the core in this way shows a system that is at once simple and subtle. Simple because there is a solid sphere and a liquid shell. Subtle because composition, pressure, temperature, and boundaries all interact to decide what is solid and what is liquid, where heat goes, and how records of growth are written into the metal. The inner core's radius, near 1,220 kilometers, and the outer core's thickness, near 2,260 kilometers, are not just figures. They define the geometry of everything that follows. The presence of iron, nickel, sulfur, carbon, and silicon is not just a chemical list. It sets density, melting behavior, and the tendency for the liquid to separate into regions that are slightly lighter or heavier. Pressures above 330 gigapascals and temperatures near 5,000 to 6,000 Kelvin are not just extreme values. They are the levers that push matter into solid or liquid states in the exact pattern we see. As this picture comes into focus, it leads naturally to the question of how we know each part and how sure we can be. The answer rests on seismic observations and on careful tracking of Earth's rotation. Those tools turn the deep interior from an idea into a mapped structure with measurable properties. How can we know what is inside Earth if we cannot go there? The answer begins with waves from earthquakes and with very careful timing of Earth's rotation. When a large earthquake happens, it sends out vibrations that travel through the planet. These vibrations are seismic waves. There are two main kinds. One kind squeezes and stretches the material it passes through. This kind is often called a pressure wave. The other kind shifts material sideways. This kind is often called a shear wave. These two kinds behave differently in solids and liquids. Shear waves do not pass through liquids. Pressure waves do pass through liquids, but their speed changes with the properties of the material. Global networks of instruments record the arrival of these waves. Each instrument is a seismometer. It senses tiny motions of the ground and writes them as a trace of time versus motion. When thousands of instruments record many earthquakes from many places, a detailed picture begins to form. The paths that go through the deep interior tell us where waves travel and how fast they travel. The times of arrival depend on the route through the planet and on the speed in each layer along that route. By comparing recorded times with calculations for many possible models of the interior, scientists decide which model fits best. One clear result is that shear waves do not cross the outer part of the core. Stations on the far side of Earth from a strong earthquake see no direct shear waves that would have passed through the core. This absence matches the behavior of a liquid layer. A liquid cannot support the sideways shifts that define a shear wave. This is a crucial clue that the outer core is liquid. Pressure waves, on the other hand, do pass through the core. Their speed slows in the liquid outer core and then increases again in the central region. That pattern shows that the central region is solid. In that solid part, pressure waves reach speeds near 11 kilometers per second. Another clear result comes from directions. In the solid center, the speed of pressure waves is not the same in all directions. It varies by a few percent. This effect has a simple name: anisotropy. The word means that a property changes with direction. In this case, the property is wave speed. The likely cause is an alignment of iron crystals that grew under conditions of strong pressure and heat. The alignment does not need to be large to produce a change of a few percent. The fact that the change is present at all is important. It says the solid center has structure written into it, a texture that formed over a long time. The exact sizes of the inner and outer core come from careful mapping of where waves are seen and where they are not seen, and from the smooth changes in speed that best match thousands of paths. The inner core's radius near 1,220 kilometers and the outer core's thickness near 2,260 kilometers are not guesses. They are the set of numbers that make wave travel times line up with the recordings over and over for earthquakes across many decades. The stations do not need to be evenly spread to do this work, but wider coverage improves confidence. As more stations were added and more earthquakes were recorded, the details sharpened. Seismic signals also include gentle, planet-wide tones after very large earthquakes. These tones are free oscillations. They are long-lasting vibrations of the whole Earth. Each tone has a frequency and a pattern that depends on the interior structure. When the core is liquid in a shell and solid at the center, certain tones split into closely spaced frequencies. The exact spacing gives more information on size and rigidity of deep layers. In this way, the core leaves marks both in sharp travel times from direct paths and in the slow ringing that follows the largest events. The two kinds of information point to the same layered structure. A second line of evidence comes from tiny changes in how fast Earth spins. The length of a day is not perfectly constant. It changes by amounts that can be as small as a few thousandths of a second. These changes are measured with very precise clocks, with radio links to distant galaxies, and with satellite tracking. The changes happen because the mantle and the core exchange torque. Torque is a push or pull that changes rotation. When the liquid core flows in certain patterns, the magnetic field and the shape of the boundary cause a small transfer of rotational influence between core and mantle. That transfer slightly speeds up or slows down the spin of the outer solid Earth. The effect is tiny, but steady enough to measure. The pattern of these day-length changes carries clues. Some variations repeat each year and each season because winds and oceans also play roles. After those parts are removed, what remains shows signals linked to motion inside Earth. There is evidence that the inner core shows slow drift relative to the mantle over spans of years to decades. The effect is small. The rate is well below 1 degree per year. Some studies see periods when the inner core moves a little faster relative to the mantle, and other periods when it moves a little slower. Other studies see a pattern that shifts around zero, suggesting a gentle oscillation. The details are still under debate because the signals are small and the measurements depend on repeated paths of waves from similar earthquakes. The shared point is that the core does not sit still with the mantle. It moves in ways that matter for how forces balance across the boundary between metal and rock. To reach these conclusions, researchers combine many techniques. They measure the first arriving waves from an earthquake, because those arrivals constrain how fast the fastest paths are. They measure later weaker waves that have bounced off layers inside Earth because those add paths that cross different parts of the interior. They look at waves that have converted from one kind to another at boundaries because those conversions happen only when a wave meets a change in properties. Each kind of observation adds a small piece. The whole picture emerges through a method called inversion. Inversion means starting from data and working back to the model that best explains it. It is not a single step. It is a long process of testing, adjusting, and comparing. The inner core's anisotropy is a key example of this process. At first, researchers noticed that some paths through the inner core gave slightly earlier arrivals than expected, while other paths gave slightly later arrivals. The pattern was not random on the globe. It depended on the angle through the center. That directional dependence is exactly what anisotropy means. To understand it, scientists proposed that the iron crystals in the inner core may have a preferred orientation that formed as the inner core grew. In solids, the pattern of atoms can guide how waves move. If many crystals align in a similar way, the effect adds up across large distances. The degree of alignment needed to match the data is small. The fact that it is detectable tells us that growth and stress in the inner core have not been uniform in all directions. Seismic evidence for a liquid outer core is also reinforced by how waves bend and reflect at the outer boundary. When a pressure wave meets the boundary from above, part of it turns into a shear wave in the mantle, and part of it continues as a pressure wave in the liquid. When a shear wave meets the boundary, it cannot enter the liquid as a shear wave, so it either reflects or converts. The patterns of reflection and conversion depend on the contrast between solid rock and liquid metal. These patterns are seen in many records and help draw a sharp line between the lower mantle and the outer core. The boundary is deep, but the signals are strong enough to be clear in many earthquakes recorded from far away. The liquid outer core also leaves a mark on the whole earth tones. One mode, commonly called the free core nutation by specialists, is a gentle wobble of Earth's rotation that depends on the shape and fluidity of the core. Observers track this wobble by watching the positions of radio sources in the sky and by following satellites. The frequency and damping of this wobble fit a model with a liquid outer core. This is a different kind of observation from seismic waves, yet it supports the same structure. The agreement builds confidence that the large-scale picture is right. It is worth asking how we can be sure that these signals really point to liquids and solids and not to some other exotic state. The key is that many independent tests agree. Shear waves do not cross the outer core, which fits a liquid shell. Pressure waves slow in that shell and speed up in the center, which fits a solid inner core. The speed change with direction in the center points to aligned crystals, which fits a solid. The free oscillations and the rotation wobbles match a liquid shell with a solid center of the measured size. Laboratory studies of iron and iron alloys under high pressure and high temperature also show melting behavior that is consistent with this arrangement. No single piece would be enough on its own, but together the pieces form a consistent whole. There are still open questions. The exact mix of light elements in the core remains uncertain. Different mixes change sound speeds and densities by small amounts, and those changes can be compared with seismic data. The texture of the inner core may vary with depth, with a top layer that differs from deeper parts. Some evidence hints at an innermost core with properties that are not the same as the rest of the inner core. If that is real, it could record an earlier growth pattern or a change in conditions. The rate and style of motion of the inner core relative to the mantle are also active topics, because they inform how forces act at the boundary and how heat leaves the deep interior. All of these measurements, from fast waves to slow wobbles, do more than outline layers. They tell us that the deep interior is not static. The liquid outer core moves, the solid inner core grows. The mantle above exchanges torque and heat with the metal below. The picture is one of steady processes that have lasted for a long time and that continue today. The speeds involved are not large by human standards. Flow in the liquid core is slow, yet it is organized on scales that match the size of the layer. The degree of crystal alignment in the inner core is small, yet it is enough to leave a clear directional mark on passing waves. The changes in day length are tiny, yet they reveal the exchange of rotational energy and momentum between layers. Knowing the structure and the motions is essential because moving liquid metal that conducts electricity can create and sustain a magnetic field. The evidence for flow, for growth, and for gentle exchange of forces across the core boundaries sets the context for understanding how a magnetic field is generated and maintained around our planet. The clues that travel through the ground and the timing signals that track the spin together point to a deep engine that is active, enduring, and measurable. Where does Earth's magnetic field get its power? It comes from slow motion in a deep ocean of liquid metal that conducts electricity very well. That ocean is the outer core. It surrounds a solid inner core made of iron. In earlier steps, we saw how waves from earthquakes show a liquid shell and a solid center. Now the focus turns to what that liquid does and how its motion makes magnetism that reaches from the center to space. The liquid metal in the outer core has very high electrical conductivity. Conductivity is a measure of how easily electric charges move through a material. In this fluid, the value sits near 1 to 2 million Siemens per meter. That means charges can flow with little resistance. When a conducting liquid moves through a magnetic field, the motion pushes charges and creates electric currents. Those currents create more magnetic field. If the flow is organized in the right way, the new field supports the original field instead of canceling it. The cycle sustains itself. This self-sustained process is the geodynamo. Flow needs a driver. In the core, there are two main drivers. The first is heat leaving the deep interior. The second is the growth of the inner core. Heat escapes from the core through the outer boundary where liquid metal meets the lower mantle. As heat leaves, the liquid below becomes slightly cooler and denser in some places and warmer and lighter in others. The lighter parts rise and the heavier parts sink. This movement is called convection. The growth of the inner core adds a chemical driver as well. When iron freezes at the boundary, it releases heat. It also leaves out lighter elements such as sulfur, carbon, and silicon. Those light elements stay in the liquid. They make the nearby liquid a little less dense. That lightened liquid rises. Both heat loss and chemical change create buoyancy, which is the tendency of lighter fluid to rise and heavier fluid to sink. Flow speeds in the outer core are slow by everyday standards. They are on the order of millimeters to centimeters per second. The layer is very thick and the motions are steady. Over long times, slow speeds still produce large organized patterns. Earth's rotation guides these patterns. Rotation tends to align flows along the spin axis and favors structures that are long in the direction from pole to pole. The result is not a random stir. It is motion with shapes and paths that last for long periods. These patterns matter because they decide where electric currents are strongest and where magnetic field is created or weakened. The geodynamo needs energy to keep going. The sources are the cooling of the core, the heat released when iron crystallizes, and the chemical energy from separating light elements from heavy iron. Together they supply several terawatts of power. A terawatt is 1 trillion watts. This power is not released in sudden bursts. It is released steadily, year after year. The steady supply keeps the liquid moving in paths that support the field. Electrical resistance in the metal tries to make currents fade, turning their energy into heat. High conductivity slows that loss. Continuous flow replaces what is lost and keeps the field from fading away. To see why conductivity and flow pattern are both important, think about how a current loop behaves. In a conductor, charges move when pushed by electric fields. A moving conductor in a magnetic field experiences a push on its charges. That push makes currents. Currents, in turn, produce magnetic field lines that thread the fluid. If currents and field lines line up in helpful ways, the pattern strengthens. If they line up in unhelpful ways, the pattern weakens. The flows in the outer core are not free to take any shape. Gravity, rotation, and the shape of the layer limit the range of patterns. Within those limits, some patterns are much better at supporting a strong, large-scale field. The boundary at the bottom of the mantle plays a major role because it controls how heat leaves the core. The mantle is solid rock on short timescales. It does not mix with the metal, but it does take heat from it. The rate of heat loss is not the same everywhere. Some regions may cool the core a little faster than others. Small differences in heat loss change how strongly the liquid below is driven. Where heat leaves faster, rising and sinking can be stronger. Where heat leaves more slowly, motion can be gentler. Over long times, these differences guide the pattern of flow. They affect where the magnetic field is created more intensely and where it is weaker. The inner core's growth shapes the engine in more than one way. Each time iron freezes at the boundary, it releases latent heat. Latent heat is the heat released or absorbed when a material changes state without changing temperature. In this case, the change is from liquid to solid. At the same time, the new solid takes in less of the light elements than the surrounding liquid contains. The leftover light elements in the nearby liquid lower its density. The result is a double push: extra heat and extra buoyancy. Both pushes arise right at the inner boundary. They make the deepest part of the outer core a natural starting place for rising motion. The details of where freezing is slightly faster or slower can also leave patterns in the flow. Those patterns can last because inner core growth is slow and steady over long spans. The scale of the outer core sets important timescales. It is thousands of kilometers thick. A parcel of liquid that rises from near the inner boundary to the outer boundary needs a long time to complete that path at millimeter to centimeter per second speeds. That means the large patterns change slowly. However, the magnetic field responds both to these slow changes and to faster, smaller adjustments in the flow. The field that emerges at the surface shows slow drift and gentle shifts over years to decades. These are signs of how the engine below evolves. The way rotation shapes flow has a direct bearing on the shape of the magnetic field. When the flow is more aligned with the spin axis, the magnetic field that results often has a strong part that points roughly from south to north through the planet. That part is called the dipole part. It is the largest scale piece of the field. Other parts of the field exist as well. They come from smaller structures in the flow and from changes in time. The blend of parts at any moment reflects the current balance of patterns in the core. When the balance shifts, the field at the surface changes shape and strength in subtle ways. There is a natural competition inside the geodynamo between building the field and losing it. Building happens when the moving conductor makes currents that add to the existing field. Losing happens because electrical resistance turns currents into heat. High conductivity in the liquid ion slows the loss because resistance is low, but it does not remove the loss. That is why a steady supply of energy from cooling and growth is needed. If those sources were weaker, the flow would weaken and the balance would tilt toward loss. The size of the core and the high conductivity give the system a long memory, so changes unfold over long periods rather than in sudden jumps. We can test the basic physics of this engine in the lab and in models, but the exact conditions of pressure and temperature in the core are unique. Still, first principles give clear guidance. Moving metal in a magnetic field creates currents. Currents create magnetic field. Rotation organizes flow. Buoyancy from heat and from composition drives motion. High conductivity lets currents persist and link far regions of the flow. These ingredients are all present in the outer core. The question then becomes how strongly each one acts and how they combine to shape the field that we observe. Evidence from the surface supports a picture of a deep engine that is steady but not fixed. The field, measured at the ground, changes a little each year. This slow change is often called secular variation by specialists. It is a reflection of the slow evolution of flow in the core. In some regions, the field grows slightly stronger. In other regions, it weakens slightly. The total change is small each year, but it adds up over decades. These drifts tell us that the engine keeps running and that its internal pattern shifts. The inner core may influence the magnetic field in other subtle ways. The alignment of iron crystals in the solid center, hinted at by seismic anisotropy, could affect how the inner boundary allows new solid to form and how light elements are expelled. If alignment varies with depth or with direction, then the pattern of growth could vary as well. That would add gentle structure to the buoyancy sources that drive the liquid. While this link is still being studied, it shows how signals in seismic data and signals in magnetic data can be related through the shared processes of growth and flow. The outer boundary with the mantle also links the deep engine to the rest of Earth. Variations in heat flow across that boundary can be tied to large structures in the mantle. Those structures change on very long timescales, but they can leave a stable imprint on where the core loses heat more quickly and more slowly. That imprint feeds back into where convection is stronger and where the magnetic field is generated more intensely. In this way, the geodynamo is not an isolated system. It is a part of the whole planet, shaped by the layers above and shaping the space around. Because flow speeds are small, and because the layer is large, the energy budget must be accounted for carefully. Several terawatts may sound large, but spread over the full volume and over very long times, it supports only gentle motion. That gentle motion is enough when the conductor is very good. A key quantity here is how far magnetic patterns are carried by the flow before they can diffuse away by resistance. In the core, that distance is large compared with the size of many flow features. That lets the flow stretch and fold magnetic field lines into shapes that reinforce the overall field. If the conductor were poor, the patterns would fade before they could amplify. The high conductivity of liquid iron under core conditions makes the difference. There are natural checks on this process. If the field grows too strong in one region, it pushes back on the flow there through magnetic forces. That feedback can redirect the flow or slow it in that area. The system seeks a balance where generation and loss are in long-term match. The result is a field that persists and changes slowly rather than racing to extremes. This balance also explains why the field can wax and wane over centuries and millennia, and why it can sometimes reorganize more deeply. Those longer episodes are part of the same engine, viewed on a longer clock. Putting these pieces together gives a coherent view. The outer core is a deep, electrically conductive fluid layer. Heat leaving the core and the steady freezing of iron at the inner boundary drive motion. The motion is guided by rotation into long-lived patterns. The moving metal creates electric currents that build magnetic field. High conductivity lets currents persist, while electrical resistance provides gentle loss that must be replaced. The energy for all of this comes from cooling, latent heat, and chemical separation, amounting to several terawatts. The inner boundary and the outer boundary set where energy and composition enter and leave, and so they steer the flow. The field that results reaches the surface and beyond, where instruments can measure its strength and shape, and where space around Earth is shaped by its presence. This deep engine is not a mystery machine. It follows clear physical rules. What makes it special is the setting: extreme pressure, high temperature, a vast volume of liquid iron, and a planet that rotates steadily. The outcome is a magnetic field that is weak at the surface, but real and measurable. It shows large-scale structure dominated by a dipole part and includes smaller features that vary from place to place. Its slow changes over years and decades are the surface signs of motion far below our feet. What does Earth's magnetic field look like where we live? At the ground, the field is gentle but real. Instruments measure its strength in units called microtesla. Typical values range from about 25 to about 65 microtesla, depending on where you are. This range is small enough that people do not feel it directly, but it is large enough for a compass to work and for sensitive tools to read it with ease. The field you stand in is the outer sign of a deep engine that moves liquid metal and makes electric currents. That engine lives in the core, but the shape we see at the surface is the result of how those currents organize and how they change over time. The broadest part of the field has a simple form with two main poles. Scientists call this a dipole. It means there is a strong part that points roughly from the southern half of the planet to the northern half, and the strength is highest near the magnetic poles. This large-scale part is not exactly aligned with Earth's spin axis. The tilt is about 11 degrees. Because of this tilt, the magnetic poles do not match the geographic poles. A compass does not point to geographic north. It points toward the magnetic north direction at your location, which is set by the field lines in your region. The position of the north magnetic pole changes with time. It drifts at a rate of roughly 40 to 60 kilometers per year. This drift is not constant from one decade to another, but in recent years it has been in that range. The drift happens because the flows in the core shift and because the balance of currents that support the field evolves. When the pole moves, the direction that compasses point to changes slightly across many places. Navigation models that show magnetic north need to be updated to account for this motion. Agencies produce global maps that are revised every few years so that ships, aircraft, and survey crews can track the current direction and strength accurately. The field at the surface also includes finer details beyond the two-pole pattern. These details are smaller scale features that change the strength and direction from place to place. Specialists sometimes call them higher harmonics. In simple terms, they are the extra pieces that make the map of the field uneven when you look closely. They come from complex flow patterns in the core and from the way the field threads through the mantle and crust. Because of these details, the field over one continent can be slightly different from the field over an ocean at the same latitude, and regional maps matter for tasks that need accuracy. One region that draws attention is called the South Atlantic Anomaly. In this broad area, centered over parts of South America and the South Atlantic Ocean, the field measured at the surface is weaker than in surrounding regions. The difference is not dramatic for people on the ground. For satellites in low orbit, the weaker field allows more high-energy particles to come close to the planet. That can raise the rate of electronic glitches and increase the dose absorbed by sensitive components. Operators plan for this by adjusting orbits, turning off non-essential functions during passes, and adding shielding. The region is a product of the same deep engine expressed through the uneven pieces of the field at the surface. Magnetic field is a vector quantity. That means it has both strength and direction. At any point on the ground, there is a number for how strong it is and an angle for which way it points. One angle tells you the horizontal direction to which a compass aligns. Another angle tells you how much the field tilts into the ground. Near the magnetic equator, the tilt is small. Near the magnetic poles, the tilt is large, and the field points steeply into or out of the ground. These geometric facts are important for practical uses. Surveyors, drillers, and pilots need to know both the strength and the direction to make corrections to instruments and to keep bearings accurate. How do we know the values at the surface with such detail? Continuous observatories on land record the field minute by minute. Survey campaigns on ships and aircraft fill in gaps over oceans and remote regions. Satellites map the field from space by carrying sensitive magnetometers. The data feed into global models that represent the field in mathematical form. These models are updated on a regular cycle to capture the slow drift that happens year by year. One example is a widely used model that is revised about every 5 years. The updates reflect changes in the core and in the near-Earth environment that affect the field measured at the ground. The slow, steady change of the field over years and decades has a simple name: secular variation. It is the surface sign of the slow changes in core flow that we discussed earlier. At one location, the strength may increase by a small amount each year. At another location, it may decrease. The direction can also shift slightly. These changes are small in a single year, but add up over a decade. They are not random noise. They follow patterns that global models can capture. The models help navigators and engineers plan with current values rather than with old maps. Local rocks also carry magnetism. Iron-rich minerals can become magnetized when they form and cool. This magnetization can add small signals to the field measured at the surface. In some places, these local signals are strong enough to matter for specialized tasks such as mineral exploration. For the global picture, the core field dominates. Mapping methods separate the broad, deep-sourced field from the shallow, local signals by their different spatial scales and by their different patterns. This separation lets the community maintain consistent global charts while also allowing local studies to focus on crustal features when needed. The field at the surface serves many roles. Compasses are the most familiar tool. They use the field to point to magnetic north. Modern navigation often uses satellites, but compasses remain useful as a simple backup and for orientation when satellite signals are blocked. Drilling operations in the subsurface use magnetic tools to keep wells on track when they cannot rely on satellite signals underground. Satellite sensors that study space weather and Earth's environment must subtract the main field to see weaker variations from currents in the ionosphere and magnetosphere. Accurate maps of the main field are essential for that subtraction. Calibration depends on knowing the baseline field at the measurement point and time. The main field is weak at the surface when compared with fields made by small magnets or by electric devices, yet its reach is global and its influence is steady. Its dipole part, with two main poles and an axis tilted about 11 degrees from the spin axis, sets the overall direction in which the field points. Its finer parts add structure that matters for operations in specific regions. The North Magnetic Pole drift at tens of kilometers per year reminds us that the field is alive, driven by the slow, deep flows of liquid iron far below. Measuring the field requires care because there are other sources of magnetic variation that ride on top of the main field. The ionosphere, which is a layer of the upper atmosphere that contains free electrons and ions, carries electric currents that change with sunlight and with activity from the sun. These currents cause daily cycles in the magnetic readings at ground observatories. The magnetosphere, which is the larger region controlled by Earth's field in space, also hosts currents that can vary quickly. During times of strong solar input, these variations can be large. To build clean maps of the main field, analysts choose quiet times, average over many days, and remove known patterns due to these external sources. The result is a calm view of the field that comes from the core. The picture that emerges connects directly back to the deep engine. The outer core's liquid iron moves slowly but steadily. That motion makes electric currents and creates a magnetic field. The field passes through the mantle and crust and appears at the surface with the strengths and patterns we measure. The fact that the field at the ground is stronger in some regions and weaker in others reflects how the deep flow is organized. The fact that the poles drift shows that the flow is changing over time. The dipole tilt tells us the axis of the field is not the same as the axis of rotation. All of these facts combined strengthen the link between surface observations and core dynamics. A careful view of the field's unequal pattern helps explain why some regions matter more for certain technologies. The South Atlantic anomaly is one such region because it lowers the barrier that normally protects low orbits from radiation. Instruments that fly through it receive more hits from high-energy particles, which can cause single-event upsets in electronics. Engineers design systems to reduce the impact, but the region still stands out in operational planning. The weak field patch is not a sign of failure. It is a natural part of a field that includes higher-order structure. As the deep engine evolves, the shape and strength of this region can change. Long-term records show that it has migrated and grown in extent in recent decades, which matches the slow shifts seen elsewhere in the field. Regional differences also affect magnetic declination, which is the angle between magnetic north and geographic north at a given spot. Declination matters for maps and for setting bearings. In some places, the angle is small. In other places, the angle is large enough that ignoring it would send a traveler off course. Maps that include declination give the value for the date of printing and show the rate of change per year. Because secular variation changes that angle slowly, navigators check current values if they need precise guidance. The tilt of the field into the ground, called inclination, matters for other tasks, such as correcting survey instruments. These angles are part of the routine language of magnetism on the ground, made practical by global models and regular updates. Satellites have improved our view of the field dramatically. They carry instruments that measure the direction and strength of the field in 3 dimensions while flying over all regions of the planet. By covering oceans and polar areas as well as land, they fill gaps left by ground observatories. They also separate the main field from temporary disturbances by sampling many places quickly. Missions dedicated to magnetic mapping have provided data that resolve the fine structure of the field and its slow change. When new maps are built, they blend satellite data with ground records to combine the strengths of both. This blending produces the most accurate global picture available at any given time. It is helpful to remember that the field we measure at the surface extends upward far beyond the air we breathe. It forms a structure in space that intercepts the flow of particles from the sun. The boundary of that structure on the sun-facing side stands at a distance of about 10 Earth radii. On the night side, it stretches into a long tail that reaches hundreds of Earth radii. The field lines guide charged particles, and currents in near-Earth space change the field on short timescales. Those changes are strongest during solar disturbances. Ground instruments and satellites observe these effects daily. To keep the focus here, we note only that the COM maps of the main field serve as a reference. Against that reference, short-term changes in near-Earth space can be seen clearly and managed by systems that depend on stable signals. Standing at the surface, we see a magnetic field that is gentle, structured, and slowly changing. Its typical strength of tens of microtesla supports simple tools and precise instruments. Its shape, controlled by a dipole tilt of about 11 degrees and by many smaller features, makes the field uneven across the globe. Its north magnetic pole drifts at tens of kilometers per year, and regions such as the South Atlantic anomaly remind us that local differences matter for operations in the sky above. The field we measure is the visible part of a deeper story written by liquid metal in motion. It also reaches outward, shaping the space around Earth where particles and fields meet. What happens to Earth's magnetic field above the air we breathe? It stretches far into space and shapes a large region around our planet. That region is called the magnetosphere. It is not a solid shell. It is a volume in space where Earth's magnetic field controls the motion of charged particles. These particles are electrons and ions. The field that we measured at the surface continues outward and meets a constant flow from the sun. That flow is the solar wind. Where the two meet, boundaries form. Those boundaries decide how much energy and how many particles enter near-Earth space at any time. The solar wind is a stream of particles that leaves the sun in all directions. It carries its own magnetic field that comes from the sun. Typical speeds are near 400 kilometers per second. Sometimes, eruptions on the sun push parts of the wind to speeds well above 1,000 kilometers per second. The density is low by everyday standards, only a few particles per cubic centimeter. Even so, over the large area near Earth, this flow carries real energy and momentum. The direction of the magnetic field in the solar wind matters. When it points southward, meaning it is opposite to Earth's northward field on the day side, more energy moves into the magnetosphere. When it points northward, less energy enters. This orientation control is a core idea for why some days are quiet and some days are disturbed. On the side that faces the Sun, the magnetosphere stands off the solar wind at a distance of about 10 Earth radii. That number changes with solar wind pressure and with the magnetic orientation that the wind carries. When the wind is faster or denser, the boundary can move closer. When the wind is slower or less dense, the boundary can move farther out. On the night side, the field lines stretch into a long tail called the magnetotail. That tail can reach hundreds of Earth radii. The tail is important because energy that enters on the day side often stores there and then releases later, driving changes that can be sudden and widespread. The first boundary that incoming particles meet is called the bow shock. It is a region where the supersonic solar wind slows down and heats up as it feels the obstacle of the magnetosphere ahead. After passing the bow shock, the solar wind flows around the magnetosphere rather than through it, unless there is a pathway for entry created by magnetic processes. The next key boundary is the magnetopause. This is the surface that separates solar wind plasma from the plasma inside the magnetosphere. Plasma is a state of matter where particles are charged and move under electric and magnetic forces. At the magnetopause, the pressure from the solar wind balances the pressure from Earth's magnetic field and from plasma inside the magnetosphere. The location of the magnetopause is not fixed. It moves in and out as the solar wind changes. Energy and particles enter through processes at the magnetopause. The most effective process happens when the solar wind magnetic field points southward. In that case, magnetic field lines from the Sun and from Earth can connect. Specialists call this magnetic reconnection. In simple words, field lines from the two regions break and join in new ways. That change opens a path. Through that path, energy and particles flow into the magnetosphere. Once inside, they travel along field lines and across field lines under the influence of electric fields that arise from the changing magnetic environment. When the solar wind magnetic field points northward, this connection is weaker and the entry is less efficient. Energy can still enter through other processes, but the rate is lower. Inside the magnetosphere, several current systems form and change during active times. One of them circles Earth in the equatorial plane and is called the ring current. It is carried by ions that drift under the combined influence of magnetic and electric fields. As this current grows stronger, it reduces the magnetic field measured at the surface near the equator. Another set of currents flows in the high-latitude ionosphere. These currents are called electrojets. They are driven by particles that stream along magnetic field lines into the upper atmosphere and by large-scale electric fields. These currents change quickly during active times and can be seen by ground magnetometers as rapid swings in the readings. When particles from space enter the upper atmosphere near the polar regions, they collide with atoms and molecules of the air. These collisions give off light. This light is the aurora. It appears in rings around the magnetic poles called auroral ovals. During quiet times, the ovals are small and near the poles. During active times, the ovals grow and move toward lower latitudes. Colors depend on which atoms are excited and at what heights, but the key process is simple. Particles from the magnetosphere are guided by field lines into the atmosphere and transfer energy that appears as light. Observers on the ground see moving curtains and arcs. Instruments on satellites see the same process as bright bands of emission around the poles. To track how disturbed the magnetosphere is, simple indices are used worldwide. One common index is called Kp. It runs from 0 to 9. It summarizes how much the ground magnetic field has changed during a 3-hour period, based on readings from many mid-latitude stations. Low numbers mean quiet times. High numbers mean strong disturbances. Another index is called DST. It focuses on the ring current. It is measured in nanotesla, which is a unit of magnetic field. When the ring current is strong, DST goes more negative. During major storms, DST can drop hundreds of nanotesla below zero. These indices give operators a common language for the level of activity, and they are useful because they connect directly to the processes in the magnetosphere. Activity builds in several steps. A southward solar wind magnetic field opens a connection on the day side. Energy flows in and is stored in the tail. Over time, the tail becomes more stressed. At some point, a reconfiguration happens in the tail that also involves magnetic reconnection. Field lines snap into new shapes and fling particles earthward and tailward. The earthward flow carries energy toward the inner magnetosphere. Some of that energy goes into the ring current. Some goes into waves in plasma that can accelerate particles further. Some goes into the ionosphere through currents that heat it and drive rapid changes. On the ground, instruments see sudden jumps. In the sky near the poles, auroras brighten and move. The magnetosphere is not closed off from the solar wind even when the solar wind magnetic field points northward. The boundary can become unstable in other ways. One such way involves layers of plasma flowing past each other at different speeds. That shear can create waves along the magnetopores. Sometimes these waves grow and mix plasma from outside with plasma from inside. Entry through this path is slower than through southward reconnection, but it can matter during long, quiet periods. Even then, small changes add up, and the system never truly stops evolving. Electric and magnetic fields inside the magnetosphere guide charged particles in paths that depend on their energy and on the strength of the field. Some particles bounce between the northern and southern hemispheres along field lines. Some drift slowly around Earth. Some are trapped for long times in regions called radiation belts. Others are lost to the atmosphere or to space. The balance between sources and losses changes with the level of activity. During strong disturbances, more particles are injected toward Earth. They can fill regions closer to the planet than usual. As conditions relax, many of these particles are removed again by collisions with the upper atmosphere or by waves that scatter them. The ionosphere is a crucial part of this system. It is the layer of the upper atmosphere where sunlight creates free electrons and ions. It conducts electricity and closes circuits that start in the magnetosphere. When currents flow in the ionosphere, they create magnetic signatures on the ground. They also affect radio waves that travel through or reflect from this layer. During active times, the ionosphere changes quickly. Electron density can rise or fall over large areas. Paths that carry radio signals can shift. These changes are not random. They follow the structure of the field and the flow of energy from the magnetosphere. The ionosphere and magnetosphere function together, with energy passing between them. Measuring these processes needs instruments in space and on the ground. Spacecraft upstream of Earth, far from the magnetosphere, sample the solar wind before it reaches us. They record speed, density, and magnetic field direction. Because they sit ahead of the bow shock along the path from the Sun, they provide tens of minutes of warning for changes that will reach the magnetosphere. Other spacecraft orbit inside the magnetosphere and in the tail. They measure fields and particles locally, showing what happens during quiet times and during storms. On the ground, arrays of magnetometers record the changing field continuously. Cameras in polar regions watch the aurora. Radars map the motion of plasma in the ionosphere. Together, these data give a full picture of how the system responds to the solar wind. The size of the magnetosphere on the day side, the length of the tail, and the level of activity are all controlled by the balance of pressure and by magnetic orientation. The pressure from the solar wind is set by its speed and density. The magnetic orientation is set by how the solar wind field points. These two controls vary as the Sun changes. The Sun has an 11-year activity cycle. During more active years, eruptions are more common. High-speed streams and large magnetic clouds pass Earth more often. During quieter years, the wind is steadier and less intense. Even within a single day, the solar wind can change quickly. The magnetosphere responds to these changes in real time. The magnetosphere also depends on the strength and shape of Earth's own field. A stronger dipole holds the boundary farther out for the same solar wind pressure. A weaker dipole allows the boundary to move closer in under the same conditions. The tilt of the dipole and the smaller features in the field shape where energy enters most efficiently and where currents flow most strongly. Over long times, as Earth's field changes slowly, the average state of the magnetosphere adjusts. This link between deep interior processes and near-Earth space is a chain that runs from the core through the surface field into the space environment. During strong disturbances, ground effects become noticeable in many ways. Magnetic readings swing by large amounts. Aurora appears at lower latitudes than usual. Radiation levels in near-Earth space rise. Powerful currents flow in the ionosphere. These are the same kinds of events that operators watch closely because they can affect technology. Even so, most days are quiet. The magnetosphere deflects and guides the solar wind around Earth. Energy trickles in and is released in small amounts. The system breathes with the Sun, sometimes gently, sometimes strongly, always under the control of basic physics that we can measure and describe. A clear view of this system helps explain simple facts that people notice. Polar lights become more frequent and brighter when the Sun is active and when the solar wind magnetic field points southward. Navigation by radio can become less reliable during those periods. Satellite instruments record more particle hits. These observations make sense when we see the magnetosphere as a boundary region shaped by two fields and two plasmas that meet. The strength of Earth's main field sets one side. The flow and field from the Sun set the other side. Where and how they connect decides the level of activity. Even though these processes are complex, the main ideas are accessible. The magnetosphere is a cavity in the solar wind, controlled by Earth's magnetic field. The bow shock slows and heats the wind. The magnetopause is the boundary where pressures balance. Energy enters most strongly when the solar wind magnetic field points southward. Inside, currents grow and fade, auroras brighten and dim, and particles are accelerated and lost. Simple indices such as Kp and dst track the level of disturbance. Ground and space instruments measure inputs and responses. The picture is a living system that reacts to changing conditions in the solar wind and that is anchored by the magnetic field that rises from deep inside Earth. As we consider this link from space back to the core, another timescale comes into view. The magnetosphere responds within minutes to hours as the solar wind changes. The field that supports it changes slowly over years to centuries. On even longer times, rocks record that the field has reorganized many times. The space around Earth then would have looked different, and the balance with the solar wind would have shifted. The chain from the core to space remains the same. but the strength and pattern at its center can move through long cycles that leave their marks in stone. Has Earth's magnetic field always been the same? The short answer is no. The field changes on many timescales. In earlier steps, we looked at changes that happen within minutes to hours in near-Earth space, and we looked at slow drifts over years to decades at the surface. Here, the clock runs much longer. Rocks carry a record that reaches back through deep time. That record shows that the field has weakened, strengthened, and even reversed direction many times. These changes are part of how a field from a moving, conducting fluid behaves over long spans. They are not sudden jumps in a single moment. They unfold over centuries to millennia and leave marks that careful measurement can read. When lava cools from a melt to a solid, tiny grains that contain iron can align with the magnetic field that is present at that time. As the rock hardens, that alignment can become fixed. The result is a remnant magnetization, which means a stable record of direction and strength. On the seafloor, new crust forms at mid-ocean ridges as molten rock rises and cools. As it cools, it records the direction of the field. The crust then moves aside as more crust forms at the ridge. Over time, this process lays down bands that carry the signature of the field's direction and strength when each band formed. When ships and submarines tow sensors across these regions, they measure patterns in the magnetization of the crust. The patterns are symmetric across the ridges and show repeated switches between periods when the field pointed roughly the same way it does today and periods when it pointed in the opposite way. This method of reading past fields is part of a field of study often called paleomagnetism. The word simply means the study of ancient magnetism. Paleomagnetism uses natural rock samples and careful laboratory procedures to extract the magnetic signal. Dating methods, such as those based on the decay of radioactive elements, give the age of the rock. Together, age and magnetic direction build a timeline. Over the last 160 million years, this timeline shows many reversals. A reversal is a change in which the magnetic poles trade places. During a reversal, compasses that would have pointed toward today's north eventually point toward today's south. The change does not happen in a single day. It can take many centuries to many millennia. The pattern of reversals is not regular. There are intervals with many reversals in a few million years. There are also long intervals with few or no reversals. One long interval with few reversals occurred during a span in the Cretaceous period. In that span, the field held one dominant direction for tens of millions of years. Other spans show more frequent switching. The point is not to memorize names or dates. The point is that the dynamo in the core can stabilize for long times, and it can also reorganize more often, depending on how flow patterns and energy sources balance. During a reversal, the strength of the global field usually drops. Measurements from lava flows and from sediments suggest that during some transitions, the field fell below 20% of its usual strength for a time. Usual strength here means the typical level outside of reversal periods in the same geologic era. The low state can last for centuries to millennia. The weakening is not the same everywhere. Some regions keep more of their field than others. In some places, the field direction wanders and changes quickly. In other places, it changes more slowly. This uneven behavior fits the idea that the field breaks into patches of different polarity, while the core's flow reorganizes. As a new order emerges, one polarity wins and the field grows back to a stronger level. A shorter and weaker event than a full reversal is often called an excursion. During an excursion, the field swings far from its usual direction and strength, but it swings back without a full reversal. One well-studied excursion happened about 41,000 years ago. During that event, some records show very low field strength and directions that differ greatly from today's. The low lasted for a few centuries to perhaps a millennium. Other records of similar age show a different pattern. This spread in the data reflects the fact that the field is not uniform across the globe during such events, and it reflects that local records can be affected by how the rock locked in the magnetic signal. Scientists handle this by sampling many sites and by checking results with different materials. The existence of many reversals and excursions raises a practical question. Do these events leave marks in the life recorded by fossils and sediments at the surface? Data from many time periods say that there is no clear link between weak field intervals and global die-offs. Extinction events in the fossil record do not line up with known reversals in a systematic way. This does not mean that weak fields had no effects at all. It means that if there were effects on biology, they were not of the kind or size that would show up as global, simultaneous losses across many groups. This is a useful bound when we think about risk from weak fields. It is helpful to ask how a reversal can happen in the first place. The geodynamo is a system where flow in a conducting fluid builds the field, while electrical resistance slowly reduces it. The field is not a single number or a single direction. It is a sum of many pieces with different sizes and shapes. The largest piece is the dipole. Smaller pieces fill in extra structure. If the patterns of flow change, the balance among these pieces can shift. The dipole can weaken while other pieces strengthen. If the dipole weakens far enough, the total field at the surface can show a mixed, patchy pattern. Over time, the dipole can grow again, but with the opposite sign. That means the north and south magnetic poles have traded places. Flow shapes this outcome. It is not set by a simple switch. It comes from many small changes that add up in the moving metal. This long-term view invites a thought experiment that helps set limits. Suppose the organized flow in the core were to stop. That is not expected under real conditions, but it is a clean way to think about what holds the field in place. Without organized flow, the currents that support the field would fade because electrical resistance turns current energy into heat. This fading is called ohmic decay. The decay time for structures as large as the core is on the order of 10,000 years. That number comes from the size of the core and from the high electrical conductivity of liquid iron. In such a decay, small-scale features would fade faster than large-scale features. The global field would become weaker and more irregular as different parts faded at different rates. In reality, a sudden stop is very unlikely. The core continues to rotate with Earth, and heat continues to leave the deep interior. Those two facts keep the fluid moving. The point of the thought experiment is to show that the field owes its persistence to continuous motion. The field is not a permanent imprint that sits in place without energy. It is a living product of a flow that must keep going for the field to remain strong and smooth at the surface. The long decay time also explains why the field can continue to exist for a while, even if flow changes reduce its ability to self-sustain. There is a buffer built into the physics. The record in rocks allows us to count reversals and to estimate durations, but it also allows us to study how the field changed during each transition. Scientists measure both direction and intensity in carefully chosen samples. They test how easily the magnetization is removed by heating or by alternating fields in the lab to separate primary signals from later overprints. They compare signals from volcanic rocks with signals from sediments laid down in lakes and in the ocean. Each type of material stores the field in a different way. By combining methods, the community builds a more robust picture of how the field behaved. Seafloor stripes are a special case because they cover large areas and because they can be tied to the rate of seafloor spreading. The age of the crust at different distances from a ridge can be estimated from known spreading rates and from dated reference points. The magnetic pattern on each side of the ridge then becomes a timeline with known spacing. This method helped confirm the idea of plate motions and provided a global record of reversals for the last many tens of millions of years. It shows times when the dipole kept one sign for long stretches and times when it switched back and forth more often. Not every change in the record is a full reversal. Some are short swings that barely leave the magnetic equator. Others are deep swings that bring the poles far from their usual places before turning back. The causes likely include changes in heat flow at the core mantle boundary, changes in how light elements are released at the inner boundary, and internal dynamics of the flow itself. The mantle above the core is not uniform. It has large structures that move very slowly. Where the mantle removes more heat, the outer core below may be driven a little harder. These patterns can persist for long times and may encourage or discourage reversals by shaping the flow. There is also evidence that the inner core's growth history could influence long-term behavior. If the inner core has regions with different crystal textures, as seismic anisotropy hints, those regions could reflect past patterns of growth and stress. Those patterns could change how and where buoyancy is added to the outer core over time. That, in turn, could shift the balance of flow patterns. This link is subtle and still under study. It shows again that the engine is a coupled system, not a simple one-parameter switch. One reason to study long-term changes is that they set the backdrop for the conditions we live in now. The field today is not the strongest it has ever been and not the weakest. It changes slowly, year by year. The North Magnetic Pole drifts. Regions such as the South Atlantic anomaly shift in shape and extent. These trends happen within the larger context of a field that has reversed many times and has passed through low states before. When we see a slow decline in global dipole strength over a century, it does not by itself mean a reversal is imminent. Reversals involve deeper reorganizations than a simple trend over a few generations. Friendly skepticism is healthy here. It keeps us focused on evidence rather than on quick conclusions. What would it mean for people and for technology if a new reversal began in the next many thousands of years, or if the field entered a low state for a long time without reversing? The geologic record helps frame an answer. Life on Earth has passed through many such intervals. No clear global extinctions line up with reversals. That points away from catastrophic outcomes driven by the field alone. At the same time, a weaker field would change how many high-energy particles reach the atmosphere and near-Earth space. It would change how the magnetosphere balances the solar wind. These changes would matter for radiation at flight altitudes, for satellite operations, and for ground systems that depend on stable fields. The scale of those effects is a practical question, not a question of fear. It can be addressed with models, with measurements, and with planning. The timeline of a reversal is long on human scales. It can take many centuries to many millennia for the field to move from one stable state to another. During that time, regions would see the field direction wander and the strength vary. Navigation that depends on magnetic maps would need more frequent updates. Instruments that subtract the main field to see weaker signals would need regular recalibration. Space weather effects would change in reach and intensity because the shape and strength of the field that shapes near-Earth space would be different. These are manageable challenges when there is awareness and when systems are built to adapt. In the end, long-term behavior of the magnetic field is a story written in stone and in seafloor. It tells us that the deep engine can reorganize. It tells us that low states have happened and will happen again. It reminds us that the field is a product of flow and that it needs energy to persist. It connects the core to the surface and to the space around Earth over times that stretch far beyond one lifetime. It also tells us that change is not sudden in this system. There is time to measure, to understand, and to respond. A clear view of this long clock sets the stage for practical questions about exposure to radiation, about air travel, and about technology in orbit and on the ground. When the field weakens, more cosmic particles reach the atmosphere, and space around Earth becomes more active for the same solar wind. These links turn a geologic story into an operational one, where thresholds and limits help guide safe choices. How does Earth's magnetic field affect the radiation that people receive? Radiation in this context means energetic particles and rays that can pass through matter and deposit energy in living tissue. A practical way to describe exposure is a unit called the sievert. It reflects how much biological effect a dose can have. Everyday levels are much lower than 1 sievert. We usually speak in millisieverts, which are thousandths of a sievert, and in microsieverts, which are millionths of a sievert. At sea level today, the average background radiation from all sources is about 2.4 millisieverts per year. Of that total, roughly 0.3 millisievert comes from cosmic rays. Cosmic rays are high-energy particles that arrive from space. When they hit the upper atmosphere, they produce showers of secondary particles that can reach the ground. The rest of the background comes from natural radioactivity in the ground, from small amounts in food and water, and from other minor sources. Earth's magnetic field helps to limit how many of the highest energy-charged particles reach the atmosphere. The field guides many particles away or forces them onto paths that do not lead straight down. When the field weakens, more of those particles can enter the atmosphere. Model studies suggest that during very low field states, the ground-level dose from cosmic rays would rise by tens of %. The increase would not be the same everywhere. It would be larger at high latitudes, where field lines are more vertical, and larger at high elevations, where there is less air above to absorb secondary particles. At low latitudes and at sea level, the change would be smaller but still present. Most people will never notice these changes directly because the absolute numbers remain small on the scale of a single day. But for planning and safety, they matter. Exposure control uses clear thresholds set by regulators. Many agencies adopt an occupational limit near 20 millisieverts per year averaged over 5 years, with no single year higher than a set cap that is only a little above that average. Limits for the public are lower. A common guidance for pregnancy is a cap near 1 millisievert for the remainder of pregnancy. These values are not targets to reach. They are ceilings that support conservative practice. They also include safety margins. The aim in operations is to stay well below them through planning, monitoring, and simple steps that reduce exposure. Aviation is where the link between the magnetic field, space weather, and people becomes a daily operational question. Commercial aircraft spend hours at cruising altitudes where the atmosphere is thinner. That means there is less shielding above. At those heights, the dose from cosmic rays is higher than at sea level. For long-haul crew, annual doses at typical cruising altitudes are often in the range of 2 to 5 millisieverts under present field strength and current solar conditions. The exact value depends on route, altitude, flight hours, and solar activity. Under a weaker field, doses on polar paths could double or triple during active solar periods. That is because more high-energy particles would reach the atmosphere over high latitudes, and flights in those regions would spend more time in air that carries more secondary particles. Short bursts from the sun can add to these levels. These bursts are called solar particle events. They often involve protons with energies high enough to reach flight altitudes, especially near the poles. During such an event, a single long flight can receive an extra dose that is measurable. Several hundred microsieverts can be added on a flight if the event is strong and the route passes through polar regions. On most days, there is no such addition. On active days, there can be. For this reason, airlines and regulators use nowcasting tools. Nowcasting means making real-time estimates of conditions that matter for operations. In this case, it means estimating the radiation dose rate along a route based on current measurements of solar particles and on the current state of Earth's magnetic field. These tools rely on monitors in space and on the ground. Spacecraft upstream of Earth measure the solar wind and the energetic particles that the sun emits. Ground detectors count secondary particles as they reach the surface. The data are combined to give dose rate maps for flight levels. Dispatchers can then decide to adjust altitude or to shift a route away from the poles. Flying at lower altitude reduces dose because there is more air above the plane to absorb secondary particles. Avoiding the polar caps also reduces dose during events because the magnetic geometry there allows easier entry for solar particles. Such changes can increase fuel use and travel time, so they are used when justified by dose estimates and by company policy. Crew planning includes simple rules to protect workers and passengers. Pregnant crew are often moved to schedules that keep dose for the remainder of pregnancy below about 1 millisievert. That can mean avoiding polar paths and choosing lower latitude routes. It can also mean favoring lower cruise altitudes when fuel and weather allow. For all crew, exposure is tracked across the year. Software tools estimate dose for each flight based on altitude, latitude, duration, and space weather level. When unusual activity starts, alerts go out through standard channels. Flight operations centers receive these alerts and can coordinate with air traffic control to change routes. The decision timeline can be short. Spacecraft that sit upstream of Earth often provide 30 to 60 minutes of lead time when a change in the solar wind is coming. For solar particle events that rise quickly, ground detectors near the poles can give confirmation within minutes. Dose nowcasts update frequently, so adjustments can be made mid-flight if needed. Passengers do not need to take special actions on normal days. The added dose from a single long flight on a quiet day is small compared with the annual average background. During an event, the airline's operational changes are the main protection. Communications from the cockpit or from the airline may note a route change or altitude adjustment as a space weather measure. These changes can also improve radio performance at high latitudes during disturbed times, which is a separate but related benefit. If you are curious about your own exposure, publicly available calculators can estimate dose for a trip by asking for route and flight level. These tools use models that take into account latitude, altitude, and solar activity. Ground-level exposure also changes with the state of the magnetic field, but the changes are gentler than at flight levels. During very low field states, the simplest expectation is a rise in ground dose by tens of %, with the largest increases at high latitudes and high elevations. For most people at mid-latitudes and near sea level, the annual change would be small in absolute terms. Still, public health agencies would watch the trend and update advice if needed. Outdoor workers at high elevations and people living in polar regions would see a larger change and would be the focus of more careful assessment. Monitoring networks would report any sustained shift in ground-level particle counts, and nuclear medicine groups would update context for background when calibrating instruments. The Sun's 11-year activity cycle is another factor in this picture. During active years, the number of solar particle events tends to rise, but the background from galactic cosmic rays tends to fall because the stronger solar wind reduces the number of the highest energy particles that enter the inner solar system. During quiet years, the opposite happens. The background from cosmic rays rises and large solar particle events are less frequent. A weaker Earth field would ride on top of this solar cycle. The result would be a modest upward shift in background doses at all times, with larger peaks during the same events that already matter today. Aviation dose management would continue to use the same tools, but alerts and route changes near the poles would likely be more common. Clarity about terms helps in conversations that mix space weather, radiation physics, and health. A solar radiation storm usually refers to a period when the flux of energetic particles from the sun is high. A geomagnetic storm usually refers to a period when currents in near-Earth space disturb the magnetic field strongly. Both can happen together, but they are not the same. For flight dose, solar particle events are often the main concern because they deliver particles that penetrate to flight levels, especially over the poles. For ground systems and for radio links, geomagnetic storms can be the main concern because they change currents and fields rapidly. Simple indices such as Kp and dst are useful signals of geomagnetic activity. Dose nowcasts use different inputs that track solar particles directly. Flight operations watch both sets of indicators to make balanced choices. Radiation risk is managed by keeping exposures as low as is reasonably achievable within the mission. In practice, that means using forecast and nowcast tools, planning routes with latitude in mind, choosing altitudes based on dose rate and fuel, and keeping good records. It also means talking openly with crew about cumulative dose and with passengers if flights are rerouted due to space weather. Training helps. When pilots and dispatchers understand how the magnetic field and the sun work together to control dose at altitude, decisions are smoother and quicker. When medical teams at airlines understand dose records, counseling for crew is consistent and calm. It is also helpful to remember that radiation is part of the natural environment. Life evolved under a background that includes cosmic rays and radioactivity in the ground. The question for operations is not how to remove radiation completely. It is how to keep avoidable exposure low without losing the benefits of air travel. A steady magnetic field from the core is a quiet partner in that effort because it reduces how many high-energy particles reach the atmosphere. When the field is weaker, more care is needed. The needed steps are known and practical. They are not dramatic. They are about route choices, altitude choices, and staying aware of current conditions. If a long interval of low field strength were to develop, the aviation community would adjust. Polar routes would be used less often during active solar periods. Some flights would shift to lower latitudes or lower altitudes for part of the route. Scheduling would include more flexibility to respond to alerts. Dose monitoring would be more widespread. Regulators might update guidance to reflect a new baseline. The tools built for present-day operations already point the way. They would be used more often and with slightly different thresholds. The path is one of adaptation rather than abrupt change. On the ground, the main public steps would be measurement and clear communication. Radiation networks already track background levels. If a trend appeared, it would be reported openly. Health agencies would update context for background radiation in their materials. This can matter for interpreting long-term studies and for calibrating instruments in clinics and labs. For people at high latitudes and high elevations, local advice might include practical suggestions for certain jobs or for certain long outdoor stays during active solar periods. These would be fine adjustments informed by data, not broad restrictions. There is a connection here to technology in space and on the ground that goes beyond dose to people. The same particles that add to dose at flight levels can damage satellite electronics. The same geomagnetic storms that drive auroras can induce currents in long power lines. The magnetic field's strength and shape set how often these stresses occur and how strong they are. A weaker field would allow more particles into near-Earth space and would change how the magnetosphere and ionosphere respond to the solar wind. Those changes raise operational questions for satellites, for power grids, and for radio systems, just as they do for aviation. The themes are similar. Measurement, modeling, and clear thresholds guide protective action. The details differ by system and by environment, and each sector has its own set of tools to keep risk controlled. What happens to our technology when the magnetic field weakens? The answer begins above our heads, where satellites work in a stream of particles and fields that change with the sun and with Earth's own magnetism. A weaker field allows more high-energy particles to enter near-Earth space and to reach orbits where many spacecraft operate. These particles carry enough energy to disturb electronics and to damage materials over time. On the ground, rapid changes in the field can drive unwanted currents in long power lines. In the air, changes in the upper atmosphere can disrupt radio and satellite navigation. Each system has its own sensitivities, and each one has tools to reduce risk. The shared point is that the strength and shape of Earth's magnetic field set how often stresses appear and how strong they can be. Satellites face two broad kinds of radiation effects. One kind happens when a single high-energy particle strikes a sensitive part of a chip. This can flip a bit in memory or logic. Engineers call this a single-event upset. It does not break the hardware. It changes a 1 to a 0 or a 0 to a 1. In some cases, the strike can trigger a short that persists inside the chip until power is cycled. Engineers call that a latch-up. The other kind of effect builds up over time. Many particles hit materials and slowly change their properties. In solar panels, this reduces power output as months and years pass. In sensors and cables, it can raise noise or make insulation weaker. A weaker magnetic field would let more particles reach orbits at all altitudes. The result would be a higher rate of bit flips and a faster pace of long-term wear. Design reduces these risks. Several millimeters of aluminum around electronics lower the number of medium-energy particles that can reach chips. Very energetic ions can still pass through, so shielding alone is not enough. Radiation-hardened chips are built to be less sensitive to single strikes. Error-correcting memory can detect and fix many bit flips as they happen. Software can scrub memory by checking and correcting each block on a schedule. Redundant systems carry 2 or 3 copies of key functions so that one can continue if another misbehaves. Watchdog timers reset a processor that has become stuck. Safe mode routines power down non-essential loads and wait for ground commands when sensors detect too many errors. These steps add mass and cost. They also add resilience. Under a weaker field, the same set of tools would still work. They would simply be called into action more often. Orbit matters. Satellites in low Earth orbit cross a region of weaker magnetic field over the South Atlantic. That region is known for raising the rate of electronic glitches. As the global field changes, the shape and reach of this weak patch also change. Operators already schedule some instruments to turn off during passes to avoid damage. Under a weaker field, affected tracks would widen and schedules would adapt. In medium Earth orbit, where navigation satellites fly, the environment includes trapped particles and bursts during storms. In geosynchronous orbit, very energetic electrons can build up charge inside insulating materials. This deep charging can suddenly discharge and create currents that flip or upset systems. A weaker field would make strong events a little more frequent and a little more intense. The response is to improve monitoring, raise design margins where mass allows, and refine fault management so that recovery is quick. Atmospheric drag is a different stress that is tied to energy input from space. During solar storms, the thermosphere, which is the upper part of the atmosphere, warms and expands. At altitudes near 400 kilometers, air density can increase by factors of 2 to 10 in strong events that already happen today. With a weaker magnetic field, energy from the solar wind would reach the upper atmosphere more often and heat it more. That does not mean every day would be stormy. It means that expansions would be more frequent and a bit stronger for the same solar wind conditions. Drag would rise more often. Orbits would decay faster. Small satellites that today stay aloft for years might stay aloft for months under repeated expansions, unless they raise their orbits or carry more propellant for drag makeup. Drag affects more than lifetime. It also changes how hard it is to know where each satellite will be in the near future. During expansions, density changes quickly. Predictions of path and position become less certain. Tracking networks update more often, and operators perform more maneuvers to maintain safe spacing. Constellations that rely on many small satellites would plan for more frequent station-keeping burns and for replacements at a higher rate. Launch schedules and supply chains would reflect this. To reduce risk, designers can choose shapes that are stable when they face drag head-on, include larger propellant margins, and plan disposal orbits that remain safe even if drag varies widely. Debris risk is linked to drag in two ways. On one hand, higher drag can clear out some debris faster by bringing it down sooner. On the other hand, higher drag creates more uncertainty in paths during events, which can raise short-term collision risk if updates are not frequent enough. The practical answer is to improve tracking coverage, share data quickly, and automate conjunction screening so that operators can respond within hours when needed. None of these steps depends on perfect forecasts. They depend on good measurements and on nimble procedures. Power grids on the ground feel the magnetic field in a different way. During strong geomagnetic disturbances, the magnetic field at the surface changes quickly. According to basic physics, a changing magnetic field can induce electric currents in long conductors. High-voltage transmission lines and their grounded transformers provide a path for these currents. The currents are slow in time. They are not the usual alternating currents of the grid. Engineers call them geomagnetically induced currents. These currents can bias transformers so that they operate partly in saturation. In saturation, transformers heat more and draw extra reactive power. Protective systems can trip lines to keep equipment safe. In a notable event in the year 1989, a transformer failure during a storm led to a 9-hour blackout in Quebec. Many factors set the outcome in any specific event, including soil conductivity, line orientation, grid configuration, and the state of the network at that time. Mitigation uses both hardware and operations. Series capacitors in transmission lines block the slow currents while allowing normal alternating current to pass. Neutral blocking devices add a barrier to the unwanted path into transformer grounds. Modern transformers can be designed to tolerate higher levels of bias without overheating. Networks can be operated with lower loading during alert periods to leave more margin. Real-time monitors measure geomagnetically induced currents at key substations. When the upstream solar wind turns southward or pressure rises sharply, operators receive alerts. They can postpone maintenance that would leave the grid in a weaker state, reduce long transfers, and prepare to reconfigure if needed. Hazard maps that combine geology, line routes, and model storms help planners place sensors and choose where to invest in protection first. Radio systems also respond to changes in the upper atmosphere. High-frequency radio links, which bounce signals off the ionosphere to reach beyond the horizon, depend on the ionized layers having the right density profile. During particle events, the lower ionosphere can become more absorbing on the sunlit side. Signals fade or fail to return to the ground along some paths. Operators then shift to other frequencies, use different paths, or move to ground cables if available. Satellite links that use frequencies in the L-band and S-band can suffer scintillation. Scintillation means that the signal at the receiver varies rapidly in phase and amplitude due to irregularities in the ionosphere. The effect can cause loss of lock or raise errors in data. Scintillation is most common near the magnetic equator after sunset and in the polar regions during disturbed times. Under a weaker field, the same solar inputs would produce broader disturbed regions more often, so outages and slowdowns would be a bit more common in those zones. Satellite navigation depends on precise timing and on the path that signals take through the ionosphere. The ionosphere delays signals by an amount that depends on electron content along the path. During disturbances, the electron content can change quickly over short distances. Single-frequency receivers must estimate the delay using a model. When the actual state differs from the model by a large amount, position errors can reach tens of meters. Receivers can also lose lock when scintillation is strong. Dual-frequency receivers solve for delay directly by comparing two signals at different frequencies. They perform better during disturbed times. Augmentation systems provide corrections and integrity messages that help users judge when the solution is accurate. Under a weaker field, the value of dual frequency and augmentation rises because disturbed conditions that stress single-frequency solutions would occur more often. Magnetic compasses provide a simple way to find direction without satellite aid. As the large-scale field weakens, compasses would become less reliable in places where local crustal magnetization is strong. The needle would still respond to magnetic forces, but the direction would be influenced more by local rocks that vary in space. This effect would not be uniform. In many regions, compasses would still be usable with updated declination values. In regions with strong local signals, maps would need to warn of anomalies. For most everyday users, satellite navigation would remain the main tool, with compasses as a backup for orientation. Tying these threads together leads to a practical view. A weaker field raises the baseline of particle flux in near-Earth space and raises the frequency of strong disturbances for the same solar wind. Satellites see more single-event effects and faster aging. Orbits in the lower thermosphere feel stronger, drag more often. Grids see more periods when induced currents are present. Radio and navigation see more frequent and wider regions of degraded performance. None of these outcomes is a sudden cliff. They are shifts in rates and in frequencies. Operators respond by adjusting design margins, by improving monitoring, and by refining procedures for alerts and recovery. Monitoring is a shared foundation. Spacecraft upstream of Earth give tens of minutes of lead time for changes in the solar wind. Spacecraft in orbit report particle fluxes and fields across many regions. Ground magnetometers show how the field is changing at the surface in real time. Ionospheric sensors, including radars and networks of satellite receivers, map electron content and scintillation. Power grids install current monitors. Airlines use dose nowcasts. Satellite operators track charging risk and prepare safe modes. The same physics that links the sun to the magnetosphere also links measurements to action. When measurements are consistent and timely, action can be calm and effective. Engineering follows simple rules that have stood the test of time. Do not rely on a single line of defense. Use shielding, hardening, and software protection together. Expect faults and make recovery automatic. Do not run systems close to their limits when external stress is rising. Give operators clear thresholds that tie to well-understood indices and measurements. practice responses so that rare events feel routine to the people who must manage them. Under a weaker field, the value of these habits increases. The steps themselves do not change. They are applied more often and with more attention. Policy choices can help. Encouraging design standards for small satellites that include minimum levels of shielding and error protection reduces failure rates for large constellations. Supporting ground networks that measure the magnetic field and the ionosphere improves warnings for all users. Planning rules for space traffic management that account for periods of high drag ease collision risk when the upper atmosphere expands. Incentives for power utilities to install blocking devices where they are most effective provide resilience without overbuilding everywhere. These choices are not tied to a specific forecast of the field. They are tied to an understanding that the baseline can shift and that preparation yields steady benefits. There is also value in being clear about uncertainty. Not every detail of how the core will evolve is known. The timeline of slow changes in the field is measured in decades to centuries. Operations happen on timescales of minutes to years. This means that planning should be flexible. It should watch indicators of long-term drift, such as the rate of dipole weakening and the growth of weak field regions, without drawing hasty conclusions. It should focus on near-term inputs, such as solar wind conditions and ground magnetic changes, to make daily decisions. This blend keeps attention on what can be measured and acted upon while tracking the background that sets the stage. The chain from the core to technology passes through the atmosphere. Energy from space heats the upper layers and changes their density and structure. Particles that enter the atmosphere change its chemistry for a time. These changes affect not only machines, but also natural systems. They touch the ozone layer, the light that reaches the surface, the animals that sense the field, and the food systems that depend on stable logistics and good weather data. The same careful approach that keeps technology operating can help us understand and manage these broader effects. How does a weaker magnetic field touch air, animals, and food? The path begins high above, where energetic particles from space meet Earth's upper air. The magnetic field steers many of these particles away. When the field is weaker, more of them reach the atmosphere. They do not stop at the edge. They dive along magnetic lines toward the polar regions and spread energy into layers that control chemistry and light. These layers respond quickly. The responses then ripple downward through systems that include climate, living things, and the ways people grow and move food. One important change happens in the stratosphere, where ozone blocks much of the sun's ultraviolet light. When a surge of particles enters this region, it creates reactive chemicals that scientists call nitrogen oxides and hydrogen oxides. For short, they often say NOx and HOx. These are not single molecules. They are families of molecules, such as nitric oxide and nitrogen dioxide for NOx, and hydroxyl and peroxy radicals for HOx. They take part in reaction cycles that destroy ozone and are not consumed by the cycle, so they act again and again until other processes remove them. After a strong solar particle event, measurements show that ozone in affected regions can drop by a few %. The drop can last for weeks before natural processes rebuild the balance. In a low field state, the same events would let particles reach wider areas. That would spread the ozone response across broader zones in the high latitudes of both hemispheres. A small drop in ozone lets more ultraviolet B light reach the surface. Ultraviolet B is a band of light with enough energy to damage skin and eyes and to affect plants and plankton. The increase is not uniform. It is larger closer to the poles during affected weeks and larger at high elevations where air is thinner. For people, This means that the same exposure time in sunlight would bring a slightly higher dose of ultraviolet B during those intervals. Simple steps such as protective clothing and eye protection remain effective. For ecosystems, the picture is broader. Laboratory and field studies show that several sensitive crop varieties can lose a few % of yield under a persistent rise in ultraviolet B. Marine and freshwater plankton at high latitudes can grow more slowly under increased ultraviolet B. These organisms form the base of food webs and help draw carbon from the surface into the deeper ocean. The changes measured in controlled studies are modest, but they point to a direction. More ultraviolet B means more stress for some species and slight shifts in timing and growth that can add up when combined with other pressures. The upper atmosphere responds to energy input in another way that matters for surface systems. The thermosphere, which is the highest layer with enough gas to matter for satellites, can warm by hundreds of Kelvin during strong events. Warming makes this layer expand. Expansion changes radio propagation paths and the density at heights where satellites fly. Many of the communication and navigation services that support weather forecasts, agriculture planning, ship routing, and disaster response depend on stable signals and on satellites that stay in predictable orbits. Disturbed conditions make those tasks harder for a time. Under a weaker field, the same solar inputs would drive these disturbances more often and over wider areas. The result would be more frequent intervals of degraded radio performance in polar regions and along bands near the magnetic equator, and more frequent needs for satellite operators to adjust paths and schedules. These are manageable challenges with present tools, but they would be present more often. Life senses and uses the magnetic field directly, not only through light and heat. Many animals carry mechanisms that allow them to detect magnetic direction or strength. Birds have light-sensitive molecules in their eyes called cryptochromes. When light excites these molecules, their internal state can be affected by the magnetic field. Experiments that gently rotate the field around captive birds show changes in orientation behavior that match changes in field direction. Some fish and turtles carry tiny crystals of magnetite in tissues. Magnetite responds to magnetic forces. Small changes in field strength can change the forces on these crystals and the signals they send to nerves. When the field is weakened in a test or when its direction is altered, these animals can lose their usual orientation for a time. Out in the wild, long migrations depend on many cues, including the sun, the stars, smells, landmarks, and the magnetic field. If the magnetic part of the guidance system becomes less reliable because the large-scale field weakens and breaks into smaller patches, error rates in navigation rise. Routes can become longer, detours more common, and energy use higher. For species that already live on tight schedules for breeding or feeding, extra time and energy costs add stress. The scale of these biological effects is still being mapped. Field studies use tracking tags to follow birds, fish, and turtles across seasons and routes. They compare paths during quiet magnetic times and during disturbed periods. They also compare routes across years as the field drifts slowly. The overall pattern that emerges is that magnetoreception is real and that it helps many species. It is not the only sense used. It adds a layer of information that improves efficiency. When that layer is blurred by a weaker, more irregular field, the cost is not a single dramatic failure. It is a steady spread of small inefficiencies that can become important when combined with habitat changes, temperature shifts, or food scarcity. This is a reason to monitor both field conditions and migration success rates together so that any link can be seen early. Food systems connect to these natural changes in more than one way. Crops grow under sunlight that includes ultraviolet B. Persistent increases in ultraviolet B can reduce yields for sensitive varieties by several % in controlled trials. Plant breeders can select for resilience and farmers can adjust practices, but the baseline matters. On top of direct effects on plants, the tools that modern agriculture uses to plan and to respond depend on data from space and on stable power and communication. Weather forecasts guide planting, irrigation, and harvest decisions. Satellite images guide water use, fertilizer application, and pest control. During disturbed periods, some of these data streams can degrade or be delayed. If low-orbit satellites re-enter more quickly because drag increases more often, replacement rates must rise to keep coverage. If power grids experience more protective trips during storms, cold storage and processing can be interrupted unless backup systems are ready. Transport and trade depend on ports, rails, and roads that use satellite navigation and communication. Even a small rise in the rate of disruption can affect timing, which flows through to costs and prices. Public health is part of this picture. People at high latitudes and high elevations would experience slightly higher ultraviolet B during weeks after large particle events if the field is weak and affected areas are wide. Health advice would emphasize the same protective steps used today, tuned to local conditions. The baseline background from cosmic rays at ground level would rise modestly in a persistent low field state, as discussed earlier. The main concern for people is not at the ground. It is at flight levels during solar particle events, which are already managed through route and altitude changes. These points keep the discussion concrete. This is not about fear. It is about understanding that small shifts in the environment call for small, well-planned adjustments. Atmospheric escape is another topic that often comes up when thinking about a weak magnetic field. Earth's upper atmosphere is thin and hot. Some particles at the top have enough energy to escape to space. Others are picked up by electric fields and carried away. Measurements and models suggest that oxygen and nitrogen escape mainly from the topmost layers at rates near 10 to the 25th particles per second. That number is large, but the atmosphere as a whole is much larger. For Earth, any measurable thinning of the bulk atmosphere due to these processes would take many thousands to millions of years. Observations at Venus provide a useful point of reference. Venus has no internally generated magnetic field. It retains a dense atmosphere. It does show strong signs of ion pickup and sputtering at the top, which are the processes that can remove particles without a protective magnetosphere. This tells us that an internal field is not the only factor that controls whether a planet can keep a heavy atmosphere. Gravity, composition, and solar input also matter. For Earth, the key is that any change in bulk air due to escape would be on timescales far beyond planning horizons for society. The effects that matter for people are the faster ones in chemistry, radiation, and technology. The chain from the sun to the surface has many steps. Energy enters near the day side of the magnetosphere and in the long tail. Particles travel along field lines into the polar caps. Currents flow in the ionosphere. The thermosphere warms and expands. The stratosphere changes chemistry. The surface sees small rises in ultraviolet B in affected regions for weeks. Animals that use the field adjust their behavior. Farmers and fishers and transport planners adjust schedules. None of these steps requires a leap. Each step is supported by measurements that can be repeated and by models that are tested against data. Awareness of these links can guide practical actions. Monitoring ozone and ultraviolet at the surface across a wide network helps track any shift in the baseline. Sampling ultraviolet B at farmland and at high-latitude coasts, where plankton thrive, gives early signs of stress. tracking migrations with tags and relating route success to magnetic conditions tests whether guidance is being impaired during weak states. Keeping Earth observation satellites healthy and replacing them promptly keeps data flowing to farms and fisheries. Investing in grid resilience and communications backup reduces the knock-on effects of space weather on storage and transport. Public information that explains what is measured and what it means keeps the tone calm and the response steady. It is sensible to ask how strong these effects would be in a prolonged low field state that lowers global field strength to well below current levels. The geologic record shows that such states have happened. It does not show large, synchronized losses of species that align with those times. That historical context is important. It tells us that life and climate have room to adapt to the kinds of shifts described here. It does not remove the need for planning. It places the emphasis on steady work that watches indicators, tests responses, and improves tools. The same patience that we use to study the core and the magnetosphere applies to ecosystems and food systems. Small changes are tracked over years, not days. Interventions are simple and tested, not abrupt. Science supports this careful approach. Laboratory studies of ozone chemistry under particle input provide rate constants for the cycles that control NOx and HOx. Field campaigns during and after solar particle events measure the actual drop in ozone and the recovery time. Long-running ultraviolet sensors at the surface show trends through solar cycles and through slow changes in the field. Biologists conduct experiments that manipulate magnetic fields around animals and plants to isolate the magnetic sense from other cues. Oceanographers measure plankton growth under controlled ultraviolet B levels and compare results to satellite-derived estimates of ultraviolet at the surface. Agronomists test crop varieties under different light conditions and identify traits that keep yields stable. Each of these threads adds a clear piece to the whole picture. Policy and practice can then draw on this base. Fisheries can plan for slight changes in plankton timing at high latitudes during active solar years. Agriculture can adjust seed choice in regions where ultraviolet B rises slightly under lower ozone after particle events. Public health can issue targeted, time-limited advice for high-latitude communities after a major event, using local ultraviolet measurements rather than broad estimates. Education can include simple explanations of how the magnetic field connects to ozone and light so that updates feel normal rather than surprising. These steps are modest. They respect the scale of the effects. They rely on measurement and on trust in data. The deeper story remains the same. A magnetic field born in moving metal reduces the number of charged particles that reach the atmosphere. When that field weakens, more energy enters the upper air. Chemistry shifts for a while, and light at the surface changes a little in select regions. Animals that sense magnetism face a noisier signal and may travel less efficiently. Food systems feel small direct effects through light and larger indirect effects through the tools that support them. The sky above is not separate from soil and sea. They are linked by flows of energy and by cycles of matter that we can measure and understand. This view naturally leads to tools that connect ideas to action. Experiments with fluids and fields test how the deep engine works. Computer models of the core, the magnetosphere, and the atmosphere link changes across layers. Networks of instruments on the ground and in space watch the field, the particles, the currents, the ozone, and the light. Operations use these streams to keep systems safe and to adapt plans. The pieces are in place. The next step is to keep refining them, to keep sharing results, and to keep decisions grounded in clear, measured signals. How do we turn deep knowledge about Earth's magnetic field into steps that help people and systems today? The path forward links laboratories, computer models, constant measurements, and clear actions. In earlier chapters, we followed the chain from the core to the surface and out into space, and we looked at effects on people, animals, and machines. Now the focus is on how to study this chain better and how to use that understanding to guide decisions in calm, practical ways. Laboratory work gives us a way to test ideas about how moving metal can create a magnetic field. Researchers use liquid metals that are safe to handle at manageable temperatures. Sodium is a common choice because it conducts electricity well and flows easily. In large tanks, pumps and impellers drive strong circulation, while the whole vessel can be set to rotate. When the flow reaches the right speed and pattern, a magnetic field appears on its own and grows. This is called self-excitation. It shows that motion in a conducting fluid can maintain a field without a permanent magnet. These experiments do not match core pressures and temperatures. They do capture the key ingredients: electrical conductivity, flow, and rotation. Sensors inside and outside the tanks record the field and the flow. By changing the way liquid moves, by adjusting rotation, and by changing the shape of the vessel, researchers see how magnetic growth responds. The lessons are direct. Patterns that twist and stretch field lines in a coherent way help the field grow. Patterns that tangle and cancel reduce growth. The results guide how we think about the balance of motions in the outer core. Computers extend this work to the full scale of Earth. Supercomputers run global simulations that represent the core as a shell of conducting fluid around a solid center, all rotating together. The codes solve equations that describe how momentum, heat, and magnetic field evolve in time. The inputs include the size of the core, the rate of rotation, the electrical conductivity of liquid iron, and estimates of how heat leaves the core into the mantle. Because the true conditions are extreme, the simulations use scaled values that preserve the important balances. Even with this scaling, the models reproduce features that match what we measure. They produce a strong dipole field with a tilted axis, they show slow drift at the surface, and they produce regions like the weak patch over the South Atlantic. They also generate reversals and excursions when the balance of flow patterns shifts. These outputs are checked against field maps from satellites and observatories and against the slow changes known as secular variation. Agreement is not perfect and does not need to be. The aim is to capture the key physics well enough that differences guide improvements. Models of the magnetosphere and atmosphere round out the picture. Codes that simulate the region where the solar wind meets Earth's field take solar wind input and compute how currents, fields, and particles respond in near-Earth space. Other codes simulate the ionosphere and thermosphere, tracking how energy inputs change electron density, winds, and temperature. These models are driven with real solar wind data when possible and with representative cases otherwise. They are checked against satellite measurements of particles and fields, ground magnetometers, ionospheric radars, and cameras that record auroras. When the model paths and strengths line up with data, confidence in forecasts grows. When they do not, the differences point to processes that need better description. Measurement is the bridge between ideas and action. On the ground, magnetometers at many latitudes record the magnetic field continuously. Networks share data in near real time. The recordings show daily cycles from the ionosphere and rapid swings during storms. Arrays of ionospheric radars map how plasma moves overhead, and networks of satellite navigation receivers measure how much the ionosphere delays signals, which reveals electron content. Cameras in polar regions watch auroras and provide a visual trace of when and where particles enter the upper atmosphere. Cosmic ray detectors count secondary particles at the surface and in the air, which supports dose nowcasting for aviation. In space, a constellation of satellites maps the main field that rises from the core. Their magnetometers are very sensitive and are calibrated carefully so that small changes year by year can be tracked. Other spacecraft travel upstream of Earth along the Sun-Earth line to sample the solar wind before it reaches the magnetosphere. They measure speed, density, and magnetic field direction. The position is far enough away that the readings give tens of minutes of warning. Inside the magnetosphere, missions sample particles and fields at many orbits, from low Earth orbit through the radiation belts out into the magnetic tail. Together, these assets form a layered observing system. Each layer senses a different part of the chain from the core to space. Turning data into useful guidance relies on methods that blend measurements with models. This blending is often called data assimilation. The idea is simple. Models predict how the system should evolve. Data show what is happening. The two are combined at each time step so that the model stays close to reality while still obeying physical laws. In practice, this approach is common in weather forecasting and now is used more and more in space weather and in mapping the main field. The benefit is that gaps in coverage can be filled with physically consistent estimates, and forecasts can be issued with clear measures of confidence. Action plans are the next link. For electric power grids, operators use hazard maps that rate exposure to geomagnetically induced currents based on ground conductivity and line routes. They install monitors at key substations to measure these currents directly. They fit series capacitors and neutral blocking devices in selected lines to block slow currents that can push transformers towards saturation. They keep extra reactive power on hand during alerts because transformers in partial saturation draw more of it. They plan for lower loading during periods when strong storms are likely, and they delay maintenance that would leave the grid with fewer paths for power to flow. Training and drills test these procedures so that teams can act calmly when alerts arrive. For aviation, flight operations centers use dose nowcasting tools that read solar particle data and predict dose rate along planned routes. When a solar particle event begins, procedures guide decisions on rerouting away from polar caps and on choosing lower cruise altitudes for selected legs. These steps reduce dose and often improve radio performance at high latitudes when the ionosphere is disturbed. The steps are time-limited. They are removed when indicators return to quiet levels. Crew dose records are kept and checked against regulatory limits with special care for pregnancy guidelines. Communication with air traffic control, with crews, and with passengers is clear and factual, so that changes are understood as routine safety practice. Satellite operators build resilience into spacecraft before launch and carry playbooks for on-orbit response. Before launch, they choose radiation-hardened components for critical functions, add shielding where mass allows the most benefit, and include error-correcting memory and watchdog timers. They design safe modes that minimize the chance of damage during charging or repeated upsets, and they test automatic recovery paths. After launch, they track anomaly rates carefully, looking for changes that might signal rising particle fluxes or aging of parts. They plan instrument schedules to turn off sensitive systems during passes through weak field regions and during storms. They carry extra propellant for drag and plan station-keeping maneuvers with room to respond to density changes in the upper atmosphere. Coordination with tracking networks ensures that conjunction warnings are received, confirmed, and acted on promptly. Radio and navigation users rely on simple rules supported by measurements. High-frequency radio operators choose frequencies and paths based on ionospheric conditions that are measured and forecast. When sunlit absorption increases during particle events, they shift bands or delay operations. Satellite navigation users who need high precision favor dual-frequency receivers and use augmentation services that provide corrections and integrity messages. When ionospheric irregularities create scintillation, operations that require steady links are rescheduled or moved to more stable regions if possible. These choices are part of routine practice in many sectors and can be expanded as conditions shift with the magnetic field. Research and engineering keep these actions effective. In the deep Earth, priorities include improving maps of heat flow at the boundary between core and mantle, narrowing the possible mix of light elements in the core, and resolving the texture of the inner core that seismic anisotropy hints at. In space weather, priorities include better models of how energy enters through the magnetopores, clearer links between solar wind structure and ground effects, and improved prediction of ionospheric density and irregularities. In technology, priorities include materials that resist radiation damage better, electronics that tolerate single-event effects with less mass, and propulsion and attitude systems that maintain orbits and pointing under higher drag and more frequent disturbances. Standards and policy help spread good practice. Design standards for small satellites can set minimum levels of shielding and error protection, which reduces failure rates in large constellations that share low orbits. Regulatory frameworks can require measurement of geomagnetically induced currents at high-risk substations and regular reporting of levels during storms. Aviation standards can formalize dose assessment methods and routing options for polar flights during events. Data sharing agreements can ensure that solar wind measurements, ground magnetic readings, and ionospheric maps are available openly and quickly to all who need them. Clear metrics make trends visible, tracking the strength of the global dipole part of the field and its rate of change helps set the long-term backdrop. Watching the drift of the magnetic poles and the size and depth of weak field regions, such as the South Atlantic anomaly, shows how regional risks evolve. Counting the frequency and depth of strong geomagnetic storms using indices such as KP and DST provides a simple way to measure the reach of space weather over years. Recording ground cosmic ray counts and flight dose rates shows whether the baseline is shifting. Mapping total electron content in the ionosphere and monitoring neutral density near 400 kilometers show how the upper atmosphere responds over time. Each metric has a clear meaning and a clear link to decisions. Together, they form a dashboard that guides planning without drama. Exercises knit these threads into skill. Grid operators run scenarios that assume a sequence of strong storms over several days. They practice reducing loads, reconfiguring networks, and restoring service under measured levels of geomagnetically induced currents. Airlines simulate rapid route changes for long-haul flights when a solar particle event begins, coordinate with air traffic management, and practice communication with crews and passengers about why changes are made. Satellite control teams rehearse transitions to safe mode, anomaly triage during heightened particle flux, and recovery to full operations when conditions improve. Agencies test cross-sector communication so that alerts travel quickly and clearly from measurement centers to decision-makers. These exercises uncover gaps and help teams build muscle memory for rare but important events. Education and public communication set the tone. When explanations connect the core, the field at the surface, the space around Earth, and daily operations in simple language, people understand why steps are taken and why they are limited in time and scope. Updates that use measured values and plain units build trust. This approach lowers the risk that normal actions will be misunderstood or that small changes in background will be seen as cause for alarm. It keeps attention on what can be observed and managed. International cooperation strengthens every link. The magnetic field covers the whole planet, and the solar wind arrives for all. Ground observatories in many countries feed shared databases. Satellites funded by different partners supply upstream solar wind data, field maps, and particle monitors. Agreements to keep these data streams open help everyone. Joint research programs speed progress on hard problems such as the mix of elements in the core or the details of how magnetic reconnection transfers energy at the boundary with the solar wind. Shared standards for reporting and for action make it easier for systems in different regions to work together during storms. It is also sensible to be honest about uncertainty. The deep interior evolves on timescales that are long for people. The magnetosphere responds on timescales that are short. The two are linked, but not in a way that allows precise long-term prediction of when a reversal will occur, or exactly how weak the field will be in a given decade. Planning should therefore be flexible. It should include triggers for review when certain indicators cross set thresholds, such as a sustained rise or fall in dipole strength beyond a chosen rate, or a growth in a regional weak field beyond a chosen size. It should emphasize readiness for space weather that we already understand and that we can measure in real time. It should invest in research that reduces uncertainty where that would change actions. Across all of this, the theme is steady progress. Laboratory experiments teach us which flow patterns grow a field. Simulations test how the core and the space environment respond as inputs change. Measurements tie ideas to reality every day and every night. Operations turn knowledge into protection with clear, small steps that add up to resilience. Policy and standards make good practice common. Metrics keep watch without hype. Exercises turn plans into skills. Cooperation and open data keep the whole system balanced and ready. The story that began with iron under extreme pressure and heat ends with people making measured choices based on clear signals. A magnetic field born in moving metal shapes the air above, the space around, and the tools we use. By studying it across scales and by acting on what we learn, we keep risks controlled and benefits high. The work is continuous, practical, and rooted in observation.